beneath an icy shell. And so it's hard to access, it's hard to get to, it's hard to even find out if there's any life there. So that leaves a few bodies that we should think about. And so let's make the problem simpler for ourselves. Let's think only about liquid water on the surface of a planet. There are only 3 bodies to think about in our solar system with regard to liquid water on the surface of a planet. And in order of distance from the sun, it's Venus, Earth, and Mars. And you want to have an atmosphere for water to be liquid. And you have to be very careful with that atmosphere. You can't have too much atmosphere, too thick or too warm an atmosphere, because then you end up too hot, like Venus, and you can't have liquid water. If you have too little atmosphere and it's too thin and too cold, you end up like Mars, too cold. So Venus is too hot, Mars is too cold, and Earth is just right. You can look at these images behind me and you can see automatically where life can survive in our solar system. It's a Goldilocks type problem, and it's so simple that a child could understand it. However, I'd like to remind you of 2 things from the Goldilocks story that we may not think about so often, but that I think are really relevant here. Number 1, if Mama Bear's bowl is too cold when Goldilocks walks into the room, does that mean it's always been too cold? Or could it have been just right at some other time? When Goldilocks walks into the room determines the answer that we get in the story. And the same is true with planets. They're not static things. They change. They vary. They evolve. And atmospheres do the same. So let me give you an example. Here's one of my favorite pictures of Mars. It's not the highest resolution image. It's not the sexiest image. It's not the most recent image. But it's an image that shows riverbeds cut into the surface of the planet. Riverbeds carved by flowing liquid water. Riverbeds that take hundreds or thousands or tens of thousands of years to form. And this can't happen on Mars today. The atmosphere of Mars today is too thin and too cold for water to be stable as a liquid. This one image tells you that the atmosphere of Mars changed, and it changed in big ways. And it changed from a state that we would define as habitable, because the 3 requirements for life were present long ago. Where did that atmosphere go that allowed water to be liquid at the surface? Well, one idea is that it escaped away to space. Atmospheric particles got enough energy to break free from the gravity of the planet, escaping away to space, never to return. And this happens with all bodies with atmospheres. Comets have tails that are incredibly visible reminders of atmospheric escape. But Venus also has an atmosphere that escapes with time, and Mars and Earth as well. It's just a matter of degree and a matter of scale. So we'd like to figure out how much escaped over time, if we can explain this transition. How the atmospheres get their energy for escape, how the particles get enough energy to escape. There are 2 ways, if we're going to reduce things a little bit. Number 1, sunlight. Light emitted from the sun can be absorbed by atmospheric particles and warm the particles. Yes, I'm dancing. But sorry, oh my God, not even at my wedding. Okay. They get enough energy to escape and break free from the gravity of the planet just by warming. The second way they can get energy is from the solar wind. These are particles, mass, material, that are spit out from the surface of the sun, and they go screaming through the solar system at 400 kilometers per second, sometimes faster during solar storms, and they go hurtling through interplanetary space towards planets and their atmospheres. And they may provide energy for atmospheric particles to escape as well. And so this is something that I'm interested in because it relates to habitability. So I mentioned that there were 2 things about the Goldilocks story that I wanted to bring to your attention and remind you about. And the second one is a little bit more subtle. If Papa Bear's bowl is too hot, and Mama Bear's bowl is too cold, shouldn't Baby Bear's bowl be even colder for following the trend? This thing that you've accepted your entire life, and you think about it a little bit more, may not be so simple. And of course, distance of a planet from the sun determines its temperature. This has to play into habitability. But maybe there's some other things we should be thinking about. Maybe it's the bowls themselves that are also helping to determine the outcome in the story. What is just right? So I can talk to you about a lot of different characteristics of these 3 planets that may influence habitability. But for selfish reasons related to my own research and the fact that I'm standing up here holding the clicker and you are not, I would like to talk for just a minute or 2 about magnetic fields. Earth has one, and Venus and Mars do not. Magnetic fields are generated in the deep interior of a planet by electrically conducting, churning, fluid material that creates this big old magnetic field that surrounds Earth, and if you have a compass, you know which way north is. Venus and Mars don't have that. If you have a compass on Venus and Mars, congratulations, you're lost. Does this influence habitability? Well, how might it? Many scientists think that a magnetic field of a planet serves as a shield for the atmosphere, deflecting solar wind particles around the planet in a bit of a force field type effect having to do with electric charge of those particles. I like to think of it instead as a salad bar sneeze guard for planets. And yes, my colleagues who watch this later will realize this is the first time in the history of our community that the solar wind has been equated with mucus. Okay, so the effect, then, is that Earth may have been protected for billions of years because we've had a magnetic field. Atmosphere hasn't been able to escape. Mars, on the other hand, has been unprotected because of its lack of magnetic field. And over billions of years, maybe enough atmosphere has been stripped away to account for a transition from a habitable planet to the planet that we see today. Other scientists think that magnetic fields may act more like the sails on a ship, enabling the planet to interact with more energy from the solar wind than the planet would have been able to interact with by itself. The sails may gather energy from the solar wind, the magnetic field may gather energy from the solar wind that allows even more atmospheric escape to happen. It's an idea that has to be tested, but the effect and how it works seems apparent, and that's because we know energy from the solar wind is being deposited into our atmosphere here on Earth. That energy is conducted along magnetic field lines down into the polar regions, resulting in incredibly beautiful aurora, if you've ever experienced them. It's magnificent. We know the energy is getting in, and we're trying to measure how many particles are getting out, and if the magnetic field is influencing this in any way. So I've sort of posed a problem for you here, but I don't have a solution yet. We don't have a solution, but we're working on it. And how are we working on it? Well, we've sent spacecraft to all 3 planets. Some of them are orbiting now, including the Maven spacecraft, which is currently orbiting Mars, which I'm involved with, and which is led here out of the University of Colorado. It's designed to measure atmospheric escape. And we have similar measurements from Venus and Earth. And so once we have all our measurements, we can combine all these together, and we can understand how all 3 planets interact with their space environment, with the surroundings, and we can decide whether magnetic fields are important for habitability or not. Once we have that answer, why should you care? I mean, I care deeply. and financially as well, but deeply. First of all, an answer to this question will teach us more about these three planets, Venus, Earth, and Mars. Not only about how they interact with their environment today, but how they were billions of years ago, whether they were habitable long ago or not. It'll teach us about atmospheres that surround us and that are close. But moreover, what we learn from these planets can be applied to atmospheres everywhere, including planets that we're now observing around other stars. For example, the Kepler spacecraft, which is built and controlled here in Boulder, has been observing a postage stamp size region of the sky for a couple of years now, and it's found thousands of planets in one postage stamp size region of the sky that we don't think is any different from any other part of the sky. We've gone in 20 years from knowing of 0 planets outside of our solar system to now having so many that we don't know which ones to investigate first. Any level will help. In fact, based on observations that Kepler's taken and other similar observations, we now believe that of the 200 billion stars in the Milky Way galaxy alone, on average, every star has at least one planet. In addition to that, estimates suggest that there are somewhere between 40 billion and 100 billion of those planets that we would define as habitable in just our galaxy. We have observations of those planets, but we just don't know which ones are habitable yet. It's a little bit like being trapped on a red spot on a stage and knowing that there are other worlds out there and desperately wanting to know more about them. Wanting to interrogate them and find out if maybe just one or two of them are a little bit like you. You can't do that. You can't go there. Not yet. And so you have to use the tools that you've developed around you for Venus, Earth, and Mars, and you have to apply them to these other situations and hope that you're making reasonable inferences from the data and that you're going to be able to determine the best candidates for habitable planets and those that are not. In the end, and for now, at least, this is our red spot right here. This is the only planet that we know of that's habitable, although very soon we may come to know of more. But for now, this is the only habitable planet, and this is our red spot. I'm really glad we're here. Thanks.
Through a forest. I'm guessing you're thinking of a collection of trees, what we foresters call a stand, with their rugged stems and their beautiful crowns. Yes, trees are the foundation of forests, but a forest is much more than what you see. And today I want to change the way you think about forests. You see, underground there is this other world, a world with infinite biological pathways that connect trees and allow them to communicate, and allow the forest to behave as though it's a single organism. It might remind you of a sort of intelligence. How do I know this? Here's my story. I grew up in the forests of British Columbia. I used to lie on the forest floor and stare up at the tree crowns. They were giants. My grandfather was a giant too. He was a horse logger, and he used to selectively cut cedar poles from the inland rainforest. Grandpa taught me about the quiet and cohesive ways of the woods, and how my family was knit into it. So I followed in Grandpa's footsteps. He and I had this curiosity about forests. And my first big aha moment was at the outhouse by our lake. Our poor dog Jigs had slipped and fell into the pit. So Grandpa ran up with his shovel to rescue the poor dog. He was down there swimming in the muck. But as Grandpa dug through that forest floor, I became fascinated with the roots. And under that, what I learned later was the white mycelium, and under that, the red and yellow mineral horizons. Eventually, Grandpa and I rescued the poor dog. But it was at that moment that I realized that that palette of roots and soil was really the foundation of the forest. And I wanted to know more. So I studied forestry. But soon I found myself working alongside the powerful people in charge of the commercial harvest. The extent of the clear cutting was alarming, and I soon found myself conflicted by my part in it. Not only that, the spraying and hacking of the aspens and birches to make way for the more commercially valuable planted pines and firs was astounding. It seemed that nothing could stop this relentless industrial machine. So I went back to school, and I studied my other world. You see, scientists had just discovered in the laboratory in vitro that one pine seedling root could transmit carbon to another pine seedling root. But this was in the laboratory, and I wondered, could this happen in real forests? I thought yes. Trees in real forests might also share information below ground. But this was really controversial, and some people thought I was crazy. And I had a really hard time getting research funding. But I persevered. And I eventually conducted some experiments deep in the forest, 25 years ago. I grew 80 replicates of 3 species, paper birch, Douglas fir, and western red cedar. I figured the birch and the fir would be connected in a below-ground web. But not the cedar, it was in its own other world. And I gathered my apparatus, and I had no money, so I had to do it on the cheap. So I went to Canadian Tire. And I bought some plastic bags and duct tape and shade cloths, a timer, a paper suit, a respirator. And then I borrowed some high-tech stuff from my university, a Geiger counter, a scintillation counter, a mass spectrometer, microscopes. And then I got some really dangerous stuff, syringes with full of radioactive carbon-14 carbon dioxide gas, and some high-pressure bottles of a stable isotope carbon-13 carbon dioxide gas. But I was legally permitted. Oh, and I forgot some stuff. Important stuff, the bug spray, the bear spray, the filters for my respirator. Oh well. The first day of the experiment, we got out to our plot, and a grizzly bear and her cub chased us off. And I had no bear spray. animals. So I came back the next day, and Mama Grizzly and her cub were gone. So this time we really got started. And I pulled on my white paper suit, I put on my respirator, and then I put the plastic bags over my trees. I got my giant syringes, and I injected the bags with my tracer isotope carbon dioxide gases. First, the birch. I injected carbon-14, the radioactive gas, into the bag of birch. And then for fir, I injected the stable isotope, carbon-13, carbon dioxide gas. I used 2 isotopes because I was wondering whether there was two-way communication going on between these species. I got to the final bag, the 80th replicate, and all of a sudden Mama Grizzly showed up again, and she started to chase me, and I had my syringes above my head, and I was sweating mosquitoes, and I jumped into the truck, and I thought, this is why people do lab studies. I waited an hour. I figured it would take this long for the trees to suck up the CO2 through photosynthesis, turn it into sugars, send it down into their roots, and maybe, I hypothesized, shuttle that carbon below ground to their neighbors. After the hour was up, I rolled down my window, and I checked for Mama Grizzly. Oh good, she's over there eating her huckleberries. So I got out of the truck and I got to work. I went to my first bag of the birch. I pulled the bag off. I ran my Geiger counter over its leaves. Perfect. The birch had taken up the radioactive gas. Then, the moment of truth, I went over to the fir tree. I pulled off its bag. I ran the Geiger counter up its needles, and I heard the most beautiful sound. It was the sound of birch talking to fir. And birch was saying, hey, can I help you? And fir was saying, yeah, can you send me some of your carbon? Because somebody threw a shade cloth over me. And then up the cedar, I ran the Geiger counter over its leaves. And as I suspected, silence. Cedar was in its own world. It was not connected into the web interlinking birch and fir. I was so excited. I ran from plot to plot and I checked all 80 replicates. The evidence was clear. The C13 and C14 was showing me that paper birch and Douglas fir were in a lively two-way conversation. It turns out at that time of year in the summer that birch was sending more carbon to fir than fir was sending back to birch, especially when the fir was shaded. And then in later experiments we found the opposite. That fir was sending more carbon to birch than birch was sending to fir. And this was because the fir was still growing while the birch was leafless. So it turns out the two species were interdependent, like yin and yang. And at that moment, everything came into focus for me. I knew I'd found something big, something that would change the way we look at how trees interact in forests, from not just competitors, but to cooperators. And I have found solid evidence of this massive below-ground communications network, the other world. Now, I truly hoped and believed that my discovery would change how we practice forestry, from clear-cutting and herbiciding to more holistic and sustainable methods, methods that were less expensive and more practical. What was I thinking? I'll come back to that. So how do we do science in complex systems like forests? Well, as forest scientists, we have to do our research in the forest, and that's really tough, as I've shown you. And we have to be really good at running from bears. But mostly, we have to persevere in spite of all the stuff stacked against us. And we have to follow our intuition and our experiences and ask really good questions. And then we've got to gather our data and then go verify. For me, I've conducted and published hundreds of experiments in the forest. Some of my oldest experimental plantations are now over 30 years old. You can check them out. That's how forest science works. So now I want to talk about the science. How were paper birch and Douglas fir communicating? Well, it turns out they were conversing not only in the language of carbon, but also nitrogen, and phosphorus, and water, and defense signals, and allulochemicals, and hormones, information. And I have to tell you, before me, scientists had thought that this below-ground mutualistic symbiosis called a mycorrhiza was involved. Mycorrhiza literally means fungus root. You see their reproductive organs when you walk through the forest. They're the mushrooms. The mushrooms, though, are just the tip of the iceberg, because coming out of those stems are fungal threads that form a mycelium, and that mycelium infects and colonizes the roots of all the trees and plants. And when the fungal cells interact with the root cells, there's a trade of carbon for nutrients. And that fungus gets those nutrients by growing through the soil and coating every soil particle. The web is so dense that there can be hundreds of kilometers of mycelium under a single footstep. And not only that mycelium connects different individuals in the forest. Individuals not only of the same species, but between species, like birch and fir. And it works kind of like the internet. You see, like all networks, mycorrhizal networks have nodes and links. We made this map by examining the short sequences of DNA of every tree and every fungal individual in a patch of Douglas fir forest. In this picture, the circles represent the Douglas fir or the nodes, and the lines represent the interlinking fungal highways or the links. The biggest, darkest nodes are the busiest nodes. We call those hub trees, or more finely, mother trees, because it turns out that those hub trees nurture their young, the ones growing in the understory. And if you can see those yellow dots, those are the young seedlings that are established within the network of the old mother trees. In a single forest, a mother tree can be connected to hundreds of other trees. And using our isotope tracers, we have found that mother trees will send their excess carbon through the mycorrhizal network to the understory seedlings. And we've associated this with increased seedling survival by 4 times. Now, we all favor our own children. And I wonder, could Douglas fir recognize its own kin? Like Mama Grizzly and her cub? So we set about an experiment. We grew mother trees with kin and stranger seedlings. And it turns out they do recognize their kin. Mother trees colonize their kin with bigger mycorrhizal networks. They send them more carbon below ground. They even reduce their own root competition to make elbow room for their kids. When mother trees are injured or dying, they also send messages of wisdom onto the next generation of seedlings. So we use isotope tracing to trace carbon moving from an injured mother tree down her trunk into the mycorrhizal network and into her neighboring seedlings. Not only carbon, but also of defense signals, and these two compounds have increased the resistance of those seedlings to future stresses. So trees talk. Through back and forth conversations, they increase the resilience of the whole community. It probably reminds you of our own social communities and our families, or at least some families. So let's come back to the initial point. Forests aren't simply collections of trees. They're complex systems with hubs and networks that overlap, connect trees, and allow them to communicate, and they provide avenues for feedbacks and adaptation. And this makes the forest resilient. That's because many hub trees and many overlapping networks. But they're also vulnerable. Vulnerable not only to natural disturbances, like bark beetles preferentially attack big old trees, but high-grade logging and clear-cut logging. You see, you can take out 1 or 2 hub trees, but there comes a point. Because hub trees are not unlike rivets in an airplane. You can take out 1 or 2 and the plane still flies. But you take out 1 too many, or maybe that one holding on the wings, and the whole system collapses. So now how are you thinking about forests? Differently? Cool. Well, so, remember I said earlier that I hoped that my research, my discoveries would change the way we practice forestry. Well, I'm going to take a check on that 30 years later here in Western Canada. This is about 100 kilometers to the west of us, just on the border of Banff National Park.